for simplifying each of these radicals. Again, we're looking to see which of those perfect squares divides or is a factor into the radicand. So what perfect square divides into 27?
9.
Alright, so 9 is the perfect square, and 27 divided by 9 is 3. So we would write this as the square root of 9 times the square root of 3. And then the square root of 9 is 3, and we leave root 3 as root 3. So 3 root 3 should be our answer for that first one. For the second one, square root of 200. What perfect square divides into 200?
100.
100. And then we rewrite this as square root of 100 times the square root of 2, because 100 times 2 gives us 200. Square root of 100 is 10, and then we leave that as the square root of 2. 10 root 2 would be our answer for the second one. And then for 72, what perfect square divides into 72?
36.
36 is our largest. And 36 times 2 is 72. Square root of 36 is 6 root 2. Did anyone use any other perfect square that went into 72? There are other ones, but it's not the highest. So if you really wanted to, again, I always say look for the highest perfect square, but if you did happen to think, oh, 9's the fastest, because I know 9 times 8 is 72, I get 3 root 8, but are we finished by stopping at 3 root 8? Is there still a perfect square that divides into 8? And yeah, so then we have to keep going. Again, that's why I always say look for the largest perfect square that divides in, because it's going to be less work. If we did 9, then we'd have to say, all right, well, 4 divides into 8 still, and the square root of 4 is 2, and now we still end up with the same answer, but again, notice how it's almost double the steps now. Okay, so always try to look for your largest perfect square. It just makes it easier for you. All right. What questions do we have from page 48? 1 to 31 odd. Any questions on those? Then we're going to look at what happens when we have some basic just exponents. How can we take the square root of these? So go ahead and write each of these radicals, and we're going to talk about how we can take the square root for each of these. Okay, so remember, when you're doing square roots, it means what times itself 2 times, in this case, equals x squared. So what times itself 2 times equals x squared? What times what equals x squared? X. Okay? So as long as you understand the definition of a square root, that first one should be pretty easy. Again, because x times x is equal to x squared. So the square root of x squared is just x. That means x to the fourth shouldn't be that difficult either. Because I'm now saying x to the what times x to the what equals x to the fourth. 2. Because remember, we're going to be adding our exponents here. So this would be x to the second. If I had x to the 8th, what would that end up being? 4. So it'd be x to the 4th times x to the 4th equals x to the 8th. So what's your trick when you have an odd when you have an even exponent and you're taking the square root? What's the little trick to it? What are you going to do with that exponent? Went from exponent of 2 to exponent of 1, exponent of 4 to an exponent of 2, exponent of 8 to an exponent of 4. Divide by 2 if you have an even exponent. Now, odd exponents aren't as easy because odd exponents you can't really divide by 2. Okay, so for odd exponents, what you're going to do is you're going to break it up using law of exponents. Okay, so you want to find the closest even and then whatever remains. So our closest even is x squared. So I'm going to break this into x squared times x to the first. Okay, because x squared times x to the first is x to the third. make sure both of them are underneath the square root, just like we broke them down before. Here we're just saying what perfect square divides into x cubed. X squared is our first perfect square that divides. Any even exponent's a perfect square. Okay, we now know the square root of x squared is x. And then there's no perfect square that goes into x to the first, so we just leave it as the square root of x. So for x to the fifth, what's our largest perfect square that divides in x to the fifth? X to the fourth. And then we times that by x to the first. And we know that the square root of x to the fourth is x squared. X to the first is not a perfect square, so we just leave it as times square root of x. Try square root of x to the 11th. So look, what's our biggest perfect square that goes in x to the 11th?
10.
X to the 10th. We're just trying to find an even exponent. So x to the 10th times x to the first. Okay? We're looking for an even exponent. We don't want the exponent to be a perfect square. We want the whole thing to be a perfect square. So we're looking for an even exponent. So what's the square root of x to the 10th? X to the 5th. And then we would leave square root of x as the square root of x. Okay, so that's how you do square roots for exponents. Right? All right, once you have that, we're going to talk about adding and subtracting radicals. Okay, so that's our next title, adding and subtracting square roots. And the key to that is that you can only add like radicals. And so we'll talk about what that means in a second. That's an example of like radicals. Both the radicals are the same. This is just like doing 7x plus 6x. You can only add x's together. If I had 7x plus 6y, I can't add them together. So what's 7x plus 6x? 13x. So, same idea, if I have 7 root 11 plus 6 root 11, right, we add those coefficients just like we did here, and we keep that radical the same. So 13 root 11. You cannot add 5 root 3 plus 2 root 2. Those are not like radicals, so you couldn't add those together. You would just leave it as is. Okay? You can only add radicals that are the same. Alright, so here's our checkpoint that we try these two. So we have 8 root 13 plus 9 root 13 as one of them. And then we have root 17x minus 20 root 17x. So these problems are nice and straightforward because you already have the like radicals. Okay? So for A, our root 13s are the same. So we're just adding our coefficients. 8 plus 9 is 17. And we leave our radical as root 13. For b, what number is really in front of that radical? A 1. So our radical is going to stay the same at 17x, square root of 17x. And our coefficient will be 1 minus 20, which is anybody? Maybe? Negative 19. So we end up with negative 19 times the square root of 17x. Okay, so those, if you have like radicals, those are pretty straightforward. If you don't have like radicals, you need to simplify each radical first. Okay? So you might want to make a note. If you do not have like radicals, you need to simplify each radical first. So you're looking for what perfect square divides into it. And then after each radical is simplified, you want to follow PEMDAS to keep simplifying it further. You should get normally you'll get like radicals after simplifying. Okay, so here's the two operations. The first one is 5 root 27 plus root 12. And our second one is 6 root 18x minus 4 root 8x. So if you notice, both of these do not have like radicals to start. So if we go off what we were saying here, it says if you do not have like radicals, you need to simplify each radical first. So I'm looking at 27. What perfect square divides into 27? That was our bell ringer. 9. So we'd have 5 times the square root of 9 times the square root of 3. All right, then we look at the square root of 12. What perfect square divides into 12? 4, thanks. Root 4 times root 3 gets us to root 12. Now this is where the PEMDAS comes in play. There's nothing in parentheses. I have to do exponents next. Remember, radicals are really exponents. So I'm taking the square root of 9 here, which is 3. So I'd write 5 times 3 times root 3. Add to that, square root of 4 is 2 root 3. Okay, so I took care of parentheses. I took care of exponents. I have to multiply and divide before I add or subtract. So I'm multiplying the 5 and the 3 next, which would give me 15 root 3 plus 2 root 3. And now I can go and do my addition. I have like radicals now of root 3, so I can actually add them, and I would end up with 17 root 3. And then for b, again, we don't have like radicals right now, so we're going to simplify each radical. So I'm bringing down the 6. What perfect square divides into 18? Matt, what do you think? What perfect square is in 18? 9. All right, so I'm going to write this as the square root of 9 times the square root of 2. 9 times 2 is 18, and there's multiplication here for that x. So I'm going to write square root of x like that. So 3 radicals for that one. That's how I get the 18x. And then minus 4. Square root of 8. What perfect square goes into 8? 4. So I have root 4 times root 2, and then again times root x. All right, PEMDAS. I do my exponents next. Square roots are exponents. So 6 times 3, because square root of 9 is 3. 2 root x minus 4. Square root of 4 is 2. Root 2 root x. And now I can do my m for multiplication. So I'll multiply the 6 and the 3 and get 18. And I can also remultiply and get 2x underneath the square root. Minus 4 times 2 is 8. And again, I'm going to multiply my radicals, 2x. Notice we have like radicals now, which is what we wanted. So 18 minus 8 is 10, root 2x. All right, I'm going to give you a few minutes to work on the following problems then. Put them on the board. If you have your book, you're more than welcome to also open your book. All right, so again, 33 to 41 odd. If you didn't get in there, that is going to be part of your homework. And then the last thing we're going to be looking at today is rationalizing denominators, okay? So if we were to have a calculator that can do this, I don't think many of your calculators can do this, but if we do have a calculator that can do this, I'll take my calculator and do this right now. We have 1 divided by the square root of 3. We get it's going to be an irrational number, so it's about 0.577. And if I then take the same thing and I do root 3 divided by 3, I get the same exact thing, about 0.577. You cannot leave a radical in the denominator, okay? It is not proper. What you need to do is you need to rationalize the denominator. So when you rationalize the denominator, that means you move the denominator to the top, okay? And this is acceptable, simplified, this is not, okay? And notice they do equal the same thing. So that's the bottom line. You cannot leave a radical in the denominator. You need to rationalize that denominator. Rationalizing means the radical goes into the top. The way we get from here to here is by multiplying by root 3 over root 3. What does root 3 over root 3 really equal? When you have the same thing on the top as the bottom, what does it always equal? 1. So this is really multiplied by 1. If you're multiplying something by 1, do you change its value? No. And so then when we do 1 times root 3, that gives us root 3. Root 3 times root 3 is root 9, which just equals 3. So that's how they are equivalent. And that's what rationalizing means. So, to rationalize, you want to do the following steps. You multiply the, I spelled that wrong, number. It should be numerator. So you multiply the numerator and denominator of the fraction by the radical that's in the denominator. So our radical that was in the denominator, for example, was root 3. So we multiply top and bottom, the numerator and denominator, by that root 3. And then we simplify the fraction. All right, so our example here, we have 5 over root 3 as one of them, and then 6 over root 12 as our second. So for 5 divided by root 3, our radical is the square root of 3. Again, we multiply by top and bottom by whatever radical is in the denominator. Root 3 is in the denominator. I'm going to be multiplying both the numerator and denominator by root 3 over 3. Because again, root 3 over root 3 really equals 1. We're not changing its value. As we multiply straight across, we get 5 root 3. And again, root 3 times root 3 is root 9. And the square root of 9 is just 3. So we are done, because there's no longer a radical in our denominator. Now for B, we have root 12. Is there a perfect square, or can we simplify root 12 before we go on? Is there a perfect square that divides into 12? Yeah. So if we can simplify, we're going to do that first. So I'm going to just rewrite root 12 as root 4 root 3, and then 2 root 3. So I end up with 6 over 2 root 3. Now, I'm still not totally done yet, because I still have a radical in the denominator. However, it makes in the end a little bit easier, because now what I can do is I can multiply just top and bottom by root 3 over root 3. So that would give us 6 root 3 in our numerator, 2, and then I have root 3, which is root 9, or just 3. Again, what should always happen is ultimately you're kind of just squaring that bottom. So whatever's underneath that radical is what you should be left with. Because again, root 3 times root 3 is root 9. That just gives us 3 then. And so that would give us 6 root 3 over 6. And since they're separated by multiplication, what's going to happen with those 6's? They cancel out. So you're left with just root 3 for this final answer. All right, last thing we're going to look at today is x minus 3 times x minus 3 and x minus 3 times x plus 3. How do we go about multiplying those? A little acronym. FOIL. So go ahead and FOIL those two and see what you got. And we're going to build off that for tomorrow. When you FOIL the first one, x times x gets us the x squared first. X times negative 3 is negative 3x. Negative 3 times x is negative 3x. Negative 3 times negative 3 is positive 9. So you're going to have like terms in the middle. Negative 6x plus 9. So that's our first way, when the signs were exactly the same. When we have opposite signs, what happens though? We have x squared plus 3x, and then our inner part is negative 3x. And we have minus 9. So what happens to those middle terms when we have opposite signs? They cancel out. So we're going to be working with this opposite signs tomorrow for what we call conjugates. Okay? So tonight, it's a little different than the board. We didn't quite get as far as I thought, but it's fine. Just do 33 to 47 odd. Okay? 33 to 47 odd.